Alright, so let's look at differential equations. Differential equations. Are equations you try to block uppercase letters all the time would be best for a foreign audience. Differential equations are equations involving derivatives. Not a totally circular definition, although it might seem that way at first. So let's say we have to now define what is a derivative. Differential equations and equations involving derivatives. What's a derivative? A derivative is a slope. That is the simplest definition. For example, let's just say, let's see, we'll use, actually I'm not even going to write an equation right now. I'm just going to draw a picture. Super simple. Draw a picture. Okay. Here's a chart. Let's say we have a function f of x. And what shall we say? It looks like this might be maybe 1. And at this point here, this looks like this might be maybe 5 or something here. So f of 1 equals 5. What's the slope? Slope is flat, so at that point the slope, and this is how we write the derivative, was this is the slope or derivative. The notation here is, let's see. Given f, a function of x, sometimes we specify with respect to x, derivative with respect to x, but since, well, let's just put it, derivative with respect to x, okay, the derivative of f of x with to x is df dx. If x is clear, then because there's no other parameter here, there's no y, there's no z, there's nothing else here, if x is clear, then we write x. So here I'm using the f tick notation because there's an x here, and because you can't take the slope with respect to anything else because there are no other variables here. There's just an x and an f of x. That might be a little more helpful. This was confusing, a little more helpful to actually write an equation, but I'm trying to draw a picture. I think it might be clearer to explain it at first with a picture. Okay, but the slope changes. Derivative changes. For example, let's take a look over here. This looks like it might be, say, -3 And it looks like at this point the value might have dropped to 3. So maybe f of -3 is 3. But what's the slope here? It's like about a 45-degree line, and that's going to give us a slope of 1. So the derivative is a slope. The derivative is a slope and is also a function itself. Notice that f's derivative varies depending on our selection of x. Just as f varies, the slope varies too. So we have the derivative as a function of f, and not just a constant. And now I might want to talk about the definition, a strict definition of a limit. You might want to actually do a bunch of examples here, but since it's just a short 20-minute lecture, I'm just going to say, okay, here's the just basic definition of a derivative, and now a differential equation. Let's see. Simple. Oops, I'm off the board here. Not sure, I just have a feeling I'm off my camera right here. So I am going to take this off. Here we are given the value of the derivative, but we're not given the value of the function. Now, so the question now becomes to solve. That's the question. What is f of x? And now probably says, what is f of x? Okay, well, f of x. F of x in this case is 1/3 x cubed plus some constant. And that's a lot of what, and that's the core of what the first year calculus class is about, is solving this very simple differential equation and relating it to a very simple mathematical problem, and that is finding the area under a curve. But that is by no means the limit of what we do with differential equations. In fact, that's all we did with them, and it probably wouldn't be all that useful. Now I gotta take some stuff down. First, I'll just take the first part down. The second derivative. Is the slope of the slope. Written d squared f. F with 2 ticks. And you'll see both notations, so it's probably best to just know both of them are. Not, this is not. No, what is it not? The square derivative. That's kind of a confusing notation. You might want to write that one. Maybe dx, df. Yeah, we have lots of notations for these things. Keep track of these. All three of these are different. Oops. All three of these are different. The second derivative is not the square of the derivative. It is not the derivative of the square. This would be taking the derivative of a completely different function. This would be taking the derivative, multiplying it by itself. The second derivative is something else entirely. It's the derivative of the derivative, the slope of the slope, or the curvature. And the notation is different for all of them. Notice when these other two that might be easy, these are the ones you don't see. You don't even see these that often. We don't use this too much. I'll get rid of this. You might see this notation if you're trying to take the derivative of a more complicated expression. This you hardly ever see. But notice there are two squares here. I almost left the one off. There's one on the top and one on the bottom. And that's the second derivative. And there's this top square from the d, and the bottom one is really, except it's not on the x, it's on the entire dx. The entire dx, which is called differential, and it's dx that is squared. So for the second derivative, you see square both the top and the bottom, and notice here you don't see a square in the bottom on either of these. So what can you do with a second derivative? The prototypical application of the first derivative is solving the area under a curve. The prototypical second derivative is the second law. Force equals mass times acceleration. But what is acceleration? Acceleration is just the rate of change, the slope is known as slope, derivative, rate of change. They're all terms that mean the same thing. It's the rate of change of the velocity with respect to time. And the velocity is the rate of change of position with respect to time. And notice here we're taking the derivative of a derivative. This v is itself a derivative, and now we're taking the derivative of a derivative. So this is actually the second derivative. d squared v dt squared. I'm sorry, d squared x. And we can write Newton's second law then in this form. F equals mass times second derivative. So, if we have some kind of expression for f, we can talk about solving this equation to find the motion of a particle. So let's do an example. Let's take a simple example of that. Consider a spring. Surface, there's a wall, there's attached, there's a spring, there's some mass. And springs, ideal springs, typically work by having some kind of rest position, and if you stretch them, they tend to pull back, and the more they stretch, the more they pull back. But also if you compress them, they'll push back. They keep trying to come back to their initial position, and an ideal spring, it's kind of a frictionless table, but an ideal spring is going to exert a force that is proportional to displacement, linearly. The more you pull it, the more it pulls back, and that is just a strict constant proportionality between the distance you pulled it and the force it's pulling back on. So if we were to just set our zero coordinate to be whatever the rest position of the spring is, then our force is going to be some spring constant k times position. So force here is k, it's actually probably going to be a negative, so we're pulling back. It could just absorb the negative sign into the constant. Let's just write it like this. F equals negative kx. And now we can substitute that into this equation. Negative kx equals m partial second derivative of x with respect to t. And now we have a differential equation, second order differential equation that we want to solve, and that would give us, the solution is going to be like this. It's going to be a sine wave. It's going to keep on going, on to infinity. We pull this thing off a little bit, and it just starts oscillating back and forth and back and forth and back and forth and back and forth. And then you're asked, well, how far did we pull it? We didn't say, did we? And the answer is no, we didn't. There's actually still some ambiguity here. This equation doesn't completely specify their system. There are missing initial conditions, or boundary conditions, as we say, that are needed in order to fully specify this thing. And if I'm doing this in a class, I think the next thing I want to throw in here, just for the heck of it, is the possibility of friction. And we're just going to have a frictional force here. We will change this up just very quickly. Frictional force is going to be proportional to velocity, probably like this. So that changes this equation like this. And now if we solve this thing, we get damping harmonic motion. A little bit more realistic. We started moving and it dies down to nothing as the friction term causes it to die out. And so that's a little more realistic, simple equation. And then when we do a lab, when we do a physics lab where you set these things up on tables and measure this stuff and actually see if you can actually physically build something that more or less behaves the way this math says it should behave. I think I just want to do one more thing, and that's just briefly to mention the difference between ordinary differential equations and partial differential equations. Ordinary single free variable. We just did one x as a function of t, and the equation was, what was it, negative kx plus mu, not a partial. T equals mass d squared x d. The point is that there's only a single parameter whose variance, time. Time changes. We want position as a function of time. A partial differential equation partial differential equations, not surprisingly, involve multiple free variables. For example, something like, let's say, electric field E as a function of x, y, and z. So we have some kind of electrical problem, but we're really a little more realistic problem. It's a three-dimensional problem. Function with the field, not just as a function of time, as a function of position, because it varies with respect to space as well. And there are three spatial coordinates, and you specify x, y, z, and t as well. And The differential equations involved there are written a little bit differently. Notation. It's going to be like this. This is the partial derivative of e with respect to x. Basically, you treat y, z, and t as if they're constants, and you just want to know what the slope is as you vary x. And then you have a partial with respect to y. You're treating now x, z, and t as constants. You just want to adjust how it behaves as you vary y. And of course, we have partials with respect to the others as well. Another example. Last example. Heat equation. And I'll just put it on here. Heat equation. Let's say we have a metal rod and we have a flame on a candlestick. Something like a flame, I guess. Okay. So we have a metal rod and we light a flame and we hold it on one side of the rod and we want to know what the temperature of the rod is. And I guess I'll just call the temperature T. T is temperature. Let's do little t is time, and x is position. So now we have temperature as a function of position and time. Big T is temperature, little t is time, and we want to know what the temperature of the rod is, not just at any one point in time or any one point on the rod. We want to know the temperature. It has two free parameters, both x and t, with position along the rod, measured like in meters perhaps, and t measured in seconds, because as time progresses, the temperature is going to change, the rod is going to heat up, there's going to be heat transport here. And if I remember correctly, I think the equation governing this is the first derivative with respect to t, and then there's some constant proportionality, and a second derivative with respect to position. And now I'm using the Greek deltas because the partial differential equation. So we have a differential equation that involves derivatives with respect to two different variables, and this is an important equation. This is the heat transport equation that does, if you actually, in physics class, spend an entire lecture talking about how we derive this thing, what the approximations and assumptions are, and where this k comes from, and again, maybe at some point do have an experiment you want to do. Might do some kind of experiment like that. I guess the main thing to say about ODEs and PDEs is that the most interesting and important physical equations are partial differential equations. Just ODEs are a little too simplistic to, dictate a lot of physical phenomena. A lot of physical phenomena requires you to have multiple parameters, but ODEs are certainly simpler. They're important from a theoretical standpoint, and what you're going to be studying in a calculus class is primarily just the simplest possible ODE, and that is just dx dt is some function of x. I've spent a lot of time just trying to solve that real simple ODE, and that ultimately leads us into the entire broader subject of analysis where you get into PDEs and such things. Okay.